This is video 4 for the Nuclei and Radioactivity unit. So in the previous unit we talked about how potassium-40 is a radioactive element that is in everyone's bodies. There is a second source of radioactivity, and it comes from an isotope called carbon-14. We also call this radiocarbon. So in carbon-14, one of the neutrons explodes, emitting an electron and a neutrino. When the electron and neutrino are emitted, the neutron then turns itself into a proton, which is kind of cool if you think about it. Neutrons becoming protons. Protons can also become neutrons. So this nucleus then has one more charge that changes the carbon into nitrogen. So on average, the half-life of carbon-14 in your bodies, half of them will explode in 5,730 years. We call this half-life. So here's a quick little graphic with carbon-14. And notice that the 14 stay the same. That's because we still have the same number of protons and neutrons. What happens, though, is that for carbon-14, it's got 6 protons and 8 neutrons. For nitrogen-14, it's got 7 protons and 7 neutrons. So you can see how one of the neutrons becomes a proton. And then what's ejected then is an electron, and I guess an antineutrino. And again, this is a beta decay. So that electron is a beta ray or a beta particle. So every gram of carbon in your body has 12 atoms of carbon-14. So that's a little bit there. It has 12 atoms of carbon-14 exploding every minute. So after every minute, you have 12 atoms of carbon-14 turning into nitrogen-14. And this assumes then that your body weight is 150 pounds and are 23% carbon. So this is like an average thing. Now, what's really fascinating is that we can use this to measure how long something has been dead. This brings us to something called the HalfLife Rule. So the half-life of carbon-14 is 5,730 years. So what this means then is that if you had 1,000 atoms of carbon-14, 5,730 years later, you would have around 500 atoms. Now, I'm going to say approximately because half-life itself is based off of probability. Nature is probabilistic. So it's natural then to assume that the remaining 500 atoms would then decay after an additional 5,730 years. So you want to say, okay, after 2 half-lives, all 1,000 of those original atoms are gone. But that's not how it works. This is based off of probability. So after that additional 5,730 years, you'd be left with 250 atoms. So let's take a look at how we can do this. So this is again for carbon-14. So after 5,730 years, we have gone through 1 half-life, and you have 1/2 of your material of the carbon-14 that's remaining. After 11,460 years, that means we've gone through 2 half-lives, and now we have 1/4 of the original material left. 17,190 years is 3 half-lives. Now we have 1/8 of the original material left. 22,920 years, that's 4 half-lives. Now we have 1/16 the original material left. So we can see then that 5,730 times n gives us the number of half-lives. And then what we're left with is 1/2 raised to the n. Now, the value for half-life is different for different radioactive isotopes. Behavior is similar, though. So for potassium, 40, the other radioactive element in your body. The half-life is 1.25 billion years. So there have been nearly 4 potassium-40 half-lives since the Earth was formed, roughly 4.6 billion years ago. So that's why we have a lot of potassium-40 left. Since the formation of the Earth, there hasn't been enough time for all of the potassium-40 to decay. Now, since they're having 4 half-lives, that means we only have 1/16 the original amount. So if we gathered up all of the potassium-40, multiplied that by 16, that's how much we had originally. So here's some radioactive elements. And let's take a look at some of their half-lives. So polonium-215. It is highly, highly reactive. It has a half-life of 0.0018 seconds, so it does not take long for all of it to decay. Polonium-216, it's a little more stable, so 0.16 of a second. Bismuth-212, about an hour. Some radioactive medicines that we have. We use elements that have a long enough half-life that we want it to be there when you mail the medicine to the hospital. But once you administer the medicine, we want it to decay quickly and get out of the patient's system. So bismuth might be a good element for some medicine. It's something that, if you make it real quick, ship it off, administer it, in a few days, it's going to be completely out of the patient's system. Sodium-24 would be another good example. It's got a half-life of 15 hours. I mean, of course, these things, you'd have to ship them very, very fast, these medicines. Iodine-131. This would be a little better. 8.14 days. Phosphorus-32. Iron-59. It's kind of weird thinking about iron being radioactive. Cobalt-60. Tritium. Remember, this is hydrogen-3. This is a hydrogen that has 1 proton and 2 neutrons. One of the reasons why we don't have a lot of tritium. It has a half-life of 12 years. It seems like a long time, but when the Earth is 4.6 billion years old, there's not going to be a whole lot of tritium left. Strontium-90 is important. That's one to remember. Strontium-90 is generally the radioactive element found in fallout after a nuclear bomb is exploded. And what makes it dangerous is that it has a half-life of 30 years. So, in some ways that's good because, after 1 or 2 centuries, all that strontium-90 is going to be gone. But what makes it bad is that, human lifespan is less than 100 years. So it's gone, an area would be gone for more than a couple generations. Now here's where we start to get into the longer ones. Radium-226. Over a millennium. Carbon-14 we've talked about. Polonium. Now polonium-239. This is one of the elements we use in nuclear power plants. Chlorine. Now, uranium-235, this is another important one. We use uranium-235 in nuclear power plants as well. 710 million years. Then uranium-238 is also an important element, one we're going to talk about, 4.5 billion. So we've had roughly one half-life for uranium-238. Now these ones on this side right here, the polonium, chlorine-36, uranium-235, it seems like those ones would be really, really dangerous because they have a half-life of so long. I mean, we're going to be stuck with those elements for a long time. But what you have to remember, since their half-lives are so long, that means they're not very reactive. The truth is, the longer the half-life, the safer the element, because it's not exploding frequently and it's not sending out fission fragments into the environment. So really, the ones you have to worry about are these ones with shorter half-lives. Strontium-90 is a very, very dangerous element because it has a very short half-life, relatively speaking. So it's going through fission very quickly, and it's spraying the area around with fission fragments, which are radioactive. Cesium-131, that's another dangerous one. Cobalt-60 would be dangerous. Now, some of these ones, like polonium, iron, phosphorus-32, where the half-life is like in weeks or days or minutes or seconds, they are super, super active. They are going through nuclear fission very, very quickly. However, because they go through fission very, very quickly, they decay very rapidly, and then they're out of the environment. So when it comes to dangerous radioactive elements, really the ones that are really dangerous are the ones that have a half-life that is relatively long, but not too long. So on the magnitude of years instead of thousands or millions or billions of years. Carbon-14, we don't have to worry about that because 5,730 years means that it's not a very active element. It's not going through fission very quickly. Now, we can use radioactivity to power satellites and other devices. So in 2006, NASA launched a satellite called New Horizons. You probably have heard this one. As of recording, the year is 2016. And this satellite was sent to Pluto, and it just recently made it to Pluto. And it sent back pictures of the dwarf planet. But you may be wondering, how was this satellite powered? Where was the electricity? Batteries and fuel cells are too heavy for a 10-year mission. So many people would say, okay, well, let's use solar panels. The problem with solar panels is that Pluto is 30 times farther from the sun than the Earth. So that means that the solar panels would be reduced by a factor of 900. So 30 times 30. So it would be reduced by a factor of 900. Now you may be wondering, why 30 by 30? That's because light has to spread out on a horizontal and a vertical plane. It's an inverse square thing. So the farther away you get, you have to square the distance. Kind of like gravity. So the sun is 900 times weaker at Pluto than it is here. So what we get then is on Earth we get roughly 1 kilowatt or 1,000 watts for a square meter. At Pluto, it's down to 1 watt per square meter. Now, solar panels, at their best, are 42% efficient. So, or actually, I'm sorry, 41%. So that means that there's only 0.41 watts or that you can only get 0.41 watts at Pluto if you're using a 1 square meter solar panel. That is not enough. It's just simply not enough electricity, not enough power to power a satellite, not one as sophisticated as New Horizons. So, for these reasons, NASA chose to use radioactivity to supply the power. So the satellite contains 24 pounds of polonium-238. It's radioactive and produces heat at a rate of about 60 watts per kilogram. So what we get is about 6,600 watts in total. We then use a thermoelectric generator, and what that is wires consisting of different metals in contact, and that's something we'll talk about later. And it converts about 7% of this heat into electricity, which gives about 460 watts of electrical power. So the combination of this is called a radioisotope thermoelectric generator, something that we call an RTG. Now the reason why NASA used polonium-238, it has a half-life of 87 years. So that means that it's actually quite reactive. It's going through fission very quickly. So this rate is fast enough for a large number of the nuclei to decay over the 10-year mission. And it produces enough high power at low weight. But the rate is low enough that the atom's only partially used up during the 10-year mission. So the power itself doesn't decrease too much over that 10-year period. So we can use radioactivity in this way to produce electricity. Now this is not enough electricity to maybe power a home. It's not a way that you would want to make gigawatts of electricity, but it's just enough to power a satellite for a long-term mission. So that's something that we can take a look at. All right, this will conclude video 4.